So Chittesh, Veni, Chandran is a final year PhD student in power quality constraint demand response at the Technical University of Dublin. He is currently working as an engineer at IRGrid in energy systems analysis, and his research interests include renewable energy integration, demand-side management, electricity market analysis, harmonic analysis, and optimization method application. Okay, thank you.
Thank you. Thanks for that. Can you hear me properly?
Yes.
Okay. So hello and welcome to the presentation on application of demand response to improve voltage regulation with a high DG penetration. Me myself, Chittesh, Veni, Chandran, and sorry, yeah. So these are my content. So I'll be going through one by one. So about the voltage problem in a radial distribution feeder, it's already, I think it's already very clear from the previous presentation, and that was a very good presentation. However, this one is more static analysis. So we are assuming that the power is all the renewable generation profile is already available and the load profile is already available. I'm just going to clear that assumption over there. So the first thing we were looking into is we wanted to actually change. We wanted to use some method to control the voltage at the end of the feeder. So we considered both over voltage and under voltage, and for over voltage scenario is actually when there is more generation under lightly loaded condition. So we want to do curtailment and curtailment of generation, and for under voltage scenario we wanted to curtail load. So in order to use curtail load, we wanted to use demand response. Now one of the problems with demand response is its acceptance with the community or the consumer acceptance. So when you are trying to violate the consumption of a consumer, the simple incentive may not always be sufficient. So we wanted to explore why this consumer acceptance is low in various demand response program, and we found that the giving a bit of options for the consumers to choose from creates more appreciation from the consumers. So what we devised is we devised an engagement plan. So we wanted to give options for the consumers to choose from to decide on the amount of participation to the load reduction. So we gave that option to the consumer. So we allocated a different consumer engagement plan. So moving forward, so what we wanted to do was, we wanted to actually manage the over voltage by generation curtailment and the under voltage by a demand response program. So we used we were assuming that the knowledge of the network is already available, the generation profile is already available, and the load profile is already available. Now we are going to use a static load flow analysis to compute the voltages, and we would be modeling the whole system in OpenDSS software, and we would be doing an unbalanced load flow. So this is a simple idea here. So we know the voltage of the receiving bus or the second bus is actually depending on the resistance and the reactance of the network, and we know already that the resistance in the distribution network is much more than the reactance. So the component which actually associate with the resistance is the active power, and so we are actually utilizing the active power curtailment method to control the voltage at the end of the feeder. So we are not actually bothered much, or we are not bothered much to regulate the reactive power here. Now, what we did was that initially for demand response, we used the mixed integer programming to compute the load reduction by individual consumers. So we formulated the total consumption, and we utilized a technique to. So initially, for any demand response, we know that there would be a demand reduction request based on which the amount of curtailment is actually done. So here, what we did was we don't have a demand reduction request. So whenever there is an over voltage, we first assume that there should be a 5% reduction to start to reduce the to manage the under voltage. Now the demand response is actually computing this amount of load reduction. It actually recalculates after the computing the load reduction. It recalculates the under voltage in the last bus, or the complete profile of the distribution feeder. Now, if the Under voltage is not cleared, so it actually increases the demand reduction to 10%. So it incrementally increases the demand reduction until a point is reached where it finds that the under voltage is actually cleared, or it is within the regulated limits. So for each of these consumers, okay, so we have a set of consumers. So the system we assumed had 74 consumers, and uh, we literally allocated them to different engagement plans. Now, what this engagement plan defines is it defines a tolerance value. So a low tolerance value means that it can the consumer would be able to go through a lot of load reduction, and a very high tolerance value would mean the consumer would not be much interested to participate in the load reduction. So we gave 4 different plans, and the first plan, Super Green Savvy plan, would be the category of consumers who would have very low tolerance value and would be able to participate in a very high manner into the load reduction. Now, so to represent this allocation, or this allocation of the demand reduction to the consumers based on the engagement plan, you can assume that this blue bar is giving the total demand reduction, and this is actually supposed to be distributed between the total end consumers who are in the network. So this should be based on their represented tolerance value. So how it would be so the way or the manner in which this optimization works, it's actually allocating each consumer a share of demand reduction based on their tolerance value. Now, yeah. So this is the low voltage distribution network. It is actually a distribution network representation which we obtained, which is in Dublin. So this had 74 consumers and their load, 74 consumers connected to this network, and we allocated randomly a certain number of solar PV generators, and to each bus we had a different ratio of generators. And each of these generators and the load associated were modeled as a fixed load or fixed generation. So which means that for a single iteration, the load and generation would be fixed. Now, we assume that throughout the feeder, the generators would be having a same generation, that is 5.75 kilowatt during which is the peak generation. Now, that is the rating of the generators which is connected to this network. And yeah, so we are actually more concerned to the last node of the network, which is the node J, or node 9. So obviously the reason is that in the radial distribution network, the more sensitive node would be the end at the end. Now, so we performed the demand response, and this is a load curve for which we actually utilized, which is an average value for which we had for different consumers. Now, we may ensure that all of the consumers would be having the same load pattern. This was to avoid any skewing of the results based due to the allocation of these load profiles. Now, you can see this consumer tolerance values keep changing depending on their participation. Now, one of the things which you can notice is that even though sometimes they go up and sometimes they go down. So one of the things which we incorporated in the algorithm was when the consumer is chosen repeatedly. Now, that's the fairness part we are coming over there. So when a consumer has very low tolerance value, he's participating for the first time into the demand response, he would be allocated a load reduction. For the next interval, the same consumer would be having a higher tolerance value, which means that he is now not willing as much he was previously to do the load reduction. So in each interval, whenever he is actually participating into the load reduction, his tolerance value increases. After a certain point, this consumer may not be suitable for doing the load reduction because his tolerance value is much higher, or there are consumers whose tolerance value is much lower. So at this interval, his tolerance value comes down. So it ensures that the same consumer may not be repeatedly chosen or for a longer period of time chosen for load reduction. Rather, every consumer in the distribution network participating in different plan would be participating based on their engagement. or based on the engagement they want or they prefer. So this gives a sense of control for each consumer to be a part of this demand response. Now, this was the maximum loading scenarios here. So generation curtailment, what we did was we already know that the last node is the one which we want to monitor. So what we did was the same principle we applied. So each time we would be reducing by 5% the generation at that node. So all the consumers who has the PV generator connected to that node or node J or the last node would have to curtail 5% when there is an over voltage. So before doing this, we performed a set of studies to see which scenario gave what kind of voltage values. So this voltage pillar one would be the first node which is connected to the transformer, and the voltage is actually set to 1 per unit over that point. Now the voltage node 9 is what we are more interested in. So when there is 100% loading or the very heavily loaded system would have we have different levels of under voltage depending on the total loading in the each phase. So phase A has a 0.86 per unit voltage level, and phase B has 0.84, and phase C also has 0.84. Similarly, we had different levels of penetration of solar, the PVDG. So and we can find that there are different scenarios where you would be having an over voltage situation. So when there is an over voltage situation, immediately there would be a 5% curtailment, and if that didn't solve the problem, it would actually go for the next 5%. So it keeps doing that until the point is reached where the over voltage is actually rectified. So this is the a consumer's generation. Who is the consumer is connected to the last node. So we applied two type of curtailment to see how much the algorithm can actually impact, and we found that by curtailing to almost 50% at certain times, we are able to achieve we bring this over voltage back to 0.9 per unit or within the limit. And if you want a tighter voltage control or voltage regulation, we can actually still achieve that by reducing the generation of the consumers connected to the end. Now, yeah. Okay. So, yeah. So this is the voltage management for the whole day for the node 9 or the last node. So we have different scenarios. So since this algorithm, which we actually proposed, had both management of over voltage and under voltage. So you can see the blue and the red lines actually give you the under voltage scenario and how this actually responds. So under voltage scenario, the voltage level at 100% loading is going below 0.9 per unit. And when we are actually regulating the voltage by reducing 10% loading, we are able to pull back that voltage to above 0.9 per unit. So I have given only phase A and phase C as a representative results. So in the over voltage scenario, we are able to curtail, we are curtailing the generation, we are able to bring back the over voltage within the regulated limits. So this, yeah. Now, the conclusion here is we can utilize demand response or any kind of active power management algorithm to control the voltage in a distribution feeder. The bottleneck for this algorithm would be that it has to have a reasonably accurate generation profile as well as the load profile. So what we end up is with if we have this load profile and generation profile, we would be able to feed it to the algorithm, and we can already know at what time we are required to do a generation curtailment, and at what time we are required to do a demand response. So according to that, we can actually initiate these signals towards the controllers, and this can be achieved, and this would in effect help the operator or the distribution system operator to have a comfortable voltage profile in the radial distribution system. Now, the other advantage here is that the demand response has multiple options for the consumers, and based on the options, the consumer's engagement is actually decided, this in effect would give a sense of control to the consumers, so that this would be positively impacting the participation of the consumers to demand response programs. So these are references. Thank you for listening, and if you have any questions, go ahead.
Great, thank you, Chittesh. Perfect timing on your presentation. Are there any questions? There's nothing in the chat window yet, but I'm sure some are coming through. I have a question. So your approach mainly relies on reducing demand, like curtailment of demand. Have you also considered load shifting so consumers can increase their demand at different hours so that they could potentially reduce more later, or vice versa?
Yeah, so we have considered that. So this was actually part of a different study which we performed, and what we did was we actually shifted the load. So in this study, we didn't actually incorporate that part. So yeah, this can be done. So essentially, a demand response would not completely curtail the consumer's load, because a consumer would prefer rather load shifting than completely curtailing the load. So load shifting during non-peak period, yeah, that can be done very without much problem in there.
Great. And you have one question in the Q&A. Do you want to look at it or have me read it?
I'll have a look. So can you speak a bit more about the next step or the challenges in the practical implementation that you still...
That was for the previous talk. There's another one from Connor McGarry.
Okay, sorry. Do you expect consumer engagement, in this case, willingness to participate in events to change if appropriately incentivized? That is a well described problem. So the issue would be mainly that the incentive which are drawn from these kind of demand response programs are not always sufficient enough. Honestly, it's not sufficient enough to motivate a consumer. So rather, there is certain studies which actually says that always it's not the monetary benefits that can motivate a consumer. Sometimes it can be, for example, an environmental concern. So you are able to represent the demand if you're changing the consumption from a peak load plant, and you're able to say that you actually saved a certain number of trees. Okay, so you actually saved 5 trees. So that would give a sense of sense of engagement for some consumers and sense of motivation for some consumers. So it's not always a single entity that would always motivate the consumers. Rather, it's a combination of all these things which can in future be a better better design for the demand response. So the primary would be enabling them to choose or give the control for the consumers rather than trying to take it from the consumer. I hope that I answered that question as well.
Yeah, thank you. Are there other questions? We have another minute or two. Okay, well, thank you very much for your presentation.
Thank you. Thanks for listening, guys.
So the next presentation is mine. So